it going, everyone? I'm CJ Cobb. I software engineer at Ripple. And today I'm going to talk to you about Project Clio. Project Clio is something I've been working on for a long time. We released version 1 at the beginning, or the end of Q2. Released our first beta in the spring. And yeah, I've been working on this project for like 2 years now, so I can talk about it a lot. Yeah, quick intro, a little bit about me. I joined Ripple in 2019. I was on the Ripple D team, like the core blockchain software that operates the XRP ledger. I added gRPC support to Ripple D as my first project. And then shortly after that, I started building reporting mode, which is sort of like the precursor to Clio. Right, I'm not going to talk about that much, but reporting mode is what we run behind our public infra, like s2.ripple.com is all reporting mode. And when we had scaling problems like last November, we deployed reporting mode across the cluster to really solve the scaling problems. So reporting mode is what I worked on first. And when that worked and proved to be successful, I spun that off in Clio, which is like a new and improved reporting mode. So yeah, when I don't write code, I like to train in martial arts. I do jujitsu, and I wrestled for a long time. So, all right, what is Clio? So Clio is a standalone server. Right? It's not the Ripple D server, it's another server that implements the Ripple D API. So Ripple D offers an API to do things like, what's my account balance, what's the status of this transaction, like what are all the transactions in the most recent ledger, all that kind of thing. It already exists, like this is how devs build their apps, right? This is how you interact with the ledger usually, or you interact with something that's already using that API. And so Clio is another server that implements that exact same API. So, you as a developer, if you're building an app, you just change the IP of where you're sending your requests and everything still works, right? The point is though, Clio is optimized for implementing this API, for handling RPC requests and for storing long-term data. Because the API allows you to look up data as of any point in time. You can look up ledgers from 10 years ago and stuff like that. And so we really optimized handling those, storing that data, processing those queries. So it's really just we had a product that already exists, the Ripple D API, but it was too slow and wasn't working that well and had problems scaling. And so we implemented a new server that is a lot better. And yeah, like I said before, the first iteration of this was Ripple D reporting mode, which is this very similar thing, but a little hacky. So yeah, Clio is the successor. So this is how it works at a basic level. There's when you run Clio, you have to run 3 things, basically. I mean, I guess other people could run the other things, but you should really run them all. So you run a Ripple D node here, right? And this connects to the XRP ledger, the peer-to-peer protocol. And this is how you stay in sync with the network, understand what ledgers were validated, understand transactions that are being propagated, all that stuff. And then you run a Clio server that connects to your Ripple D server and continuously extracts data from the Ripple D server, right? So this extraction happens over gRPC, which is protobuf, right? And that's a little more efficient than the current Ripple D API that uses JSON, right? Protobuf, it's all in blobs, right? Whereas JSON, you have to represent blobs as hex, right? And that takes up twice as much space. So yeah, we continuously extract data from Ripple D. Every time a ledger is validated, we extract some data, and then Clio takes that data, does a little bit of transformation, and writes it to its own database. And right now we support Cassandra and ScyllaDB. They're actually sort of the same database. It's just a different implementation of the same query language and schema, right? So in Clio, we don't have 2 separate code paths, one for Cassandra, one for Scylla. We just have one code path. I would like to expand this to support more database options. And I tried to originally. We were supposed to support Postgres as well. But it's actually pretty hard to store the ledger data in a database because it's a lot of data. It's several terabytes. In Clio, it's about 4 terabytes or a little less. Postgres can't really handle 4 terabytes of data. Once you pass 500 gigabytes, Postgres doesn't really perform that well. So I really wanted to use Postgres because it's a little bit easier to use than Cassandra or Scylla, but it just wasn't panning out. So I would like to add support for an embedded database, but that has some caveats. So I'll talk about that later. But anyways, this is the architecture. So there's Clio extracts data from Ripple D, writes it to its database, and then clients just query Clio, right? They send their RPCs to Clio instead of Ripple D. And Clio doesn't talk to Ripple D to handle the request. It just talks to its own database, gets the data it needs, and returns it to the client. So in this way, it sort of protects Ripple D, right? So Ripple D is no longer handling RPC requests at all. right? And this is really good because RippleD has a tough job already. RippleD has to stay in sync with the network, has to process transactions, has to come to consensus, right? And when you hit it really hard with RPC traffic, it makes it harder for RippleD to do those jobs. And at some point, RippleD actually desyncs with the network, in which case it can't do anything, right? And desyncing with the network has like a cascade effect because it's on the peer-to-peer network, right? If your RippleD desyncs, it has peers. All of a sudden, those peers can't use it as a resource to stay in sync, right? And it makes it harder for those peers to stay in sync. So you really don't want RippleD to desync from the network. Last November, when we had all the scaling issues, what was happening is RippleD was losing sync with the network like all over the place, right? So Clio protects RippleD and makes sure it can stay in sync with the network and process transactions and just do less work, right? Some things do need to go to RippleD still, certain RPCs, such as submitting a transaction. There's no way Clio can submit the transaction because the transaction has to hit the peer-to-peer network at some point or another, right? And so the way it does that is it sends it to RippleD. So it'll accept the transaction, says, oh, here's the submit command, takes the transaction, and then forwards it to RippleD. RippleD will try to apply it to its open ledger. If everything is okay, it'll submit it to the network, and then it returns a response to Clio, which Clio then propagates back to the client, right? We do this for a couple other things. Submit is the main command that you have to do this for, but other things like open ledger data, right? Data that hasn't yet been validated, you have to talk to RippleD for, and so clients can ask Clio to ask RippleD. Fees, right? Clio doesn't know anything about fees. That's another thing that's really just on the peer-to-peer network, and it'll ask RippleD for the fee and then give it back to the client. So that's a basic setup, but we really designed this to operate at scale, right? RippleD can handle some RPCs without a problem, right? But when you really pound it with RPCs, when you run some public service, right? We run s2.ripple.com, which gets 8,000 RPC requests per second, right? RippleD can't really handle that well. And even one Clio node is gonna have a little bit of trouble with 8,000 requests per second, especially depending on your hardware. So we really wanted to design a piece of software that could scale horizontally in response to increased traffic, that you could run this API as a web service, right? Not just you running it for your app, but you could handle an arbitrary number of connections and requests at any time, right? Just infinite throughput. And so the way we did this is since the data is already in Cassandra or Scylla, which can be operated on a remote server across the network somewhere, you can spin up other Clio nodes in front of the same database, right? And they'll come up right away. You don't have to copy any data. They don't have to sync or anything like that. They're just a shell sitting in front of the data set that's already populated and being populated. So in this setup, say you have 10 Clio servers, one of them will be talking to RippleD, like we showed on the last slide, and extracting the data, keeping the data set up to date. And then the other ones just sit there and read, and they can handle the same requests from clients, but they just don't have to actually extract any data from RippleD. So we run this in S2. So if we're getting more requests and we're oh wow, we need more servers, these servers are slowing down, we just spin up more Clio servers in front of the same data set. This is super fast, right? If you do this with RippleD uses an embedded database, so you can't do this that quickly. You have to copy all the data over, right? And for full history, these services usually support full history. That's 20 terabytes. So if you're doing this with RippleD and you want to spin up a new RippleD server behind your service, you got to copy 20 terabytes of data to a new machine, and then it can come online, right? So this is much better because you just deploy a new EC2 instance, comes on in a minute, bam, and then it's up and running. So that's how that works. And you can also so I had this slide where Clio talks to RippleD. You can also have multiple RippleDs over here for greater availability. So that way if one of your RippleDs crashes or loses sync or something like that, Clio can talk to the other ones, and it can even load balance the requests across them, stuff like that. So that's that. The other interesting thing about Clio is we changed the data model. So RippleD uses a SHA map, which is sort of like a Merkle tree, right? Every blockchain software uses something like a Merkle tree, right? And the purpose of the Merkle tree, or the SHA map, is to be used on the peer protocol. So nodes can prove to another node that a transaction is in a certain ledger, right? So I don't know if everyone knows how Merkle trees work, but say I have a ledger and I know what the root of the transaction Merkle tree is, right? Another node can just like give me a transaction and the path from leaf to root, and then I can know, oh yeah, that transaction's in that ledger, right? So this is used on the peer protocol. But this is large, right? So for full history, which means storing all data from the beginning of the ledger, beginning from Genesis, takes 20 terabytes, right? And this is just growing and growing over time. 20 terabytes is so much data. It's really hard to get a machine with 20 terabytes of storage, right? And it has to be fast storage. RippleD needs like a really fast SSD, an NVMe drive, right? 20 terabytes of NVMe drive, that's really hard to come by, right? So what we did is we changed the data model. And what I did is, Clio is not on the peer protocol, does not participate in this verification process of verifying if transactions are in specific ledgers. So I just removed all these upper nodes, all these inner nodes here, all these red nodes, and you just have the leaf nodes, because the data itself is only at the leaves, right? The transaction itself, or the account object, is just at the leaves. Everything else is just for verification. Clio doesn't use that, so we removed it. And this dramatically reduced the size of the data. And Clio full history is only 3.5 terabytes, right? This is super workable, right? Like I have 4 terabytes of fast SSD on my machine, on my work machine. I have 2 NVMe drive slots, right? And I got a 2 terabyte drive in each slot. So this is fine. This is not that hard to procure, right? There's so many, cloud instances with that much, SSD space. So this is really great, and this also saves us a lot of money when we run these services that we don't have to pay for nearly as much storage. It also saves a lot of space with a single ledger, right? A single SHA map, a ledger represented as a SHA map with the Merkle tree format, is 18 gigabytes. That's what RippleD has to keep in memory, basically. And RippleD is a memory hog. It usually uses at least 20-something gigabytes of memory, right? And if you're sending RPC requests to it, it can use up to 64 gigabytes. Whereas the flat map, right, this thing where we remove the inner nodes, is only 6 gigabytes. This is a really small data set. That's really not that big. Almost every machine has 6 gigabytes of RAM that you could use. So there's that. The other benefit to this is fetching a node. Fetching a node out of the SHA map requires walking down the tree, right? You have to start at the root and get all the way to the leaf. For RippleD, this could be 64 nodes deep. And with Clio, when the data is in Cassandra, somewhere over the network, each one is a network round trip, right? So if you round trip 64 times, it's a couple milliseconds every round trip, you're looking at 100 milliseconds to fetch one object, right? Whereas with Clio's data set, or with data model without these inner nodes, with just the flat map here, it's just one read. You just fetch it 1 or 2 milliseconds, there's the data. So the only caveat here is that you can't verify individual objects anymore with without the SHA map, but you can take the whole ledger and recreate the SHA map and verify your data is correct, right? And we do this all the time. This is one of my main ways of testing Clio. So I take the whole ledger, recreate the SHA map, and rehash it and make sure the hash is correct. So this is what the schema looks like. It's just a compound key here, where this key is the object ID. And the sequence, this is every time the object is modified, we write a new row to the database, all right? Because the tree is also in RippleD how you sort of look up different versions of the same object, because you started a different root. So if I'm looking up the count as of ledger 1, I start at the root of ledger 1. At ledger 10, I start at the root of ledger 10, right? But we can't do that if we don't have a tree, so we just have a compound primary key. The timer is not running for the talk. I have no idea where I am on time, by the way. Yeah. I'm trying to keep going. So yeah, anyways, this is what we did. And we cached, it doesn't look like I have that much time. Okay, so we can cache this whole thing in RAM, which is really great. This is one of the best things. So we save all this space on disk, right? And we can represent full history with a lot less space, way more efficient, way more tractable in terms of operating it. And we can also cache a single ledger in RAM, right? And this is really great because I said it only takes about 6 gigabytes. So this is what Clio does. Every Clio node has the validated ledger, the most recent ledger, in RAM in full, right? And this is really great because almost every single query for state data wants the validated ledger. very, very few people like query like, what was my account balance like 10 years ago or a month ago? Like very few people care. It's like 98% of queries just hit this cache. So this cache has like a 98% hit rate. It's like super, super high hit rate. And it's super simple because all we're doing is just like keeping track of the most recently validated ledger. I'm not like doing some LRU cache and keeping track of when things are accessed. It's just the ledger closes. Some things were deleted from the ledger, delete them from cache. Some things were modified and added, put them in the cache, and that's it, right? So that happens like once every 4 seconds. It takes like a couple milliseconds to do that. And then in that time, besides the update, the cache is static. Right? It's not being changed at all because we're not updating like access time or anything like that. It's just sitting there. So all the reads can truly happen in parallel. So it's really massive parallelism. This is one of my favorite parts of the code, actually. It's like super simple, not that much lines of code, really easy to reason about, but it has a huge impact on performance. So yeah, so that's that. We have a bunch of different tables here, but most of the data is just it's either the objects, the transactions, or the ledger headers. All our other tables are just like indices, basically, to be able to access the objects in the raw data in the way we want. Like something might be like, I'm gonna talk about it later, like NFTs, right? NFTs are stored in the objects table, but you can't look up an NFT by its ID in the objects table because it's stored in like a page that's associated with the account, right? And you don't know, if you just have the token ID, you don't know what the account is. So we have a special table that has a token ID and it maps it to an account, right? And then you go into the objects table and grab the actual NFT. Another one is like account transaction history, right? We have a transactions table, but you're not gonna scan the whole table looking for transactions that mention a certain account. So we have a special table that maps an account to like a list of hashes that are transaction hashes, and we go back into that first table. So this is interesting. So like, the reason we need these indices is because we use Cassandra, and for Cassandra, like you can't just write arbitrary queries. You need to design, like figure out what your queries are beforehand and build special indices, right? But if you like put this same data in something like BigQuery, say like objects, transactions, and ledgers, that's all you would need, and you could write any query, execute any query you want on just that data, right? And it would work. It might be slightly slow, but if you're just trying to do analytics, like it'll work, right? Because BigQuery can do like a full table scan, right? Pretty quickly, or quick enough at least. So something to think about. Clio, we can't do that. So other performance optimizations, I'll just go quickly through this. All the database reads are totally async, so we receive a request, make a call to the database, and we just yield on that thread and pick up new requests. So we're never like waiting on the database to respond. This allows us to get like really high CPU utilization. Yeah, I think I'm running out of time, so I'm gonna skip through this. We run a lot of public infra at RippleX, like I was talking about before. We run S1 and S2, which are the full history servers. You can hit Clio directly at S2-Clio. And then we run like public-facing RPC nodes for DevNet and testnet. This altnet is a testnet. Not going to demo this because I don't think this is that interesting. This is kind of interesting though. So whenever you query any of these nodes, Clio, RippleD, reporting mode, any of that, you're actually like trusting that that node is giving you the correct answer, right? If it's not your node, you have no idea if the operator is running correct code, what code they're running, like if they didn't modify the code to do something malicious or just accidentally modifying the code. If you're running a package, right, you don't really know like what code does that binary actually map to, right? And even if you are running your own node, right, and you read the code and you can understand the code and you think it's correct, you could have made a mistake, right, and not actually read the code correctly, right? Because the API doesn't give back some proof in its response. You say, give me the account, and it says, here's the account, right? It doesn't give you back the Merkle tree proof. Like, that could be wrong, right? I think that's kind of interesting. But anyways, I just wanted to mention that. But like, there's levels of trust here. So when you hit our service, you have more trust. When you're running your own node, you need less trust, but there's always some trust. Okay, so talk about how it works. That's mostly all performance stuff. But now, since Clio is like a standalone RPC server and that's its only responsibility, we can actually extend the API and do things that RippleD can't do or won't do. Sometimes RippleD won't do things because it's like too expensive performance-wise. Sometimes RippleD won't do things just because it's going to make the code super complex, right? RippleD is already a big piece of software. If we just add whatever API we want into RippleD, it'll be unwieldy very quickly, right? And this is bad because RippleD is supposed to process transactions. If there's a bug in transaction processing, it's a huge problem. But Clio is just serving RPCs, right? The stakes are like a little bit lower in a sense, and there's just less code to begin with because all it does is handle RPCs, so you can expand the API however much you want. So yeah, basically during the extraction process and the transformation process, we can do all kinds of things to create different tables to support different queries, right? And we did that with, I'm gonna skip ahead. We did that with, or we're doing that with a couple things. We're doing that for NFTs, so you can look up tokens by their ID. We're doing that with another thing with NFTs where you can get transaction history for NFTs. Say like, give me all the transactions that affected this NFT. RippleD does not support that. RippleD won't support that, right? Because it doesn't need to. It doesn't need to support that to process transactions. It would just be excess stuff for RippleD. I added support for ledger diffs, which is like, give me all the objects that changed as part of applying the transactions in this ledger. So, and we're considering more things, right? Because this is like, you can just add whatever you want. It has to be designed carefully because we have to write the tables and write the queries, and you have to load all the data in. But something like IOU volume or historical price data is something we're considering adding as well. So NFT info. So this is a good case study. So like I said before, the only way to retrieve an NFT in RippleD is to know its owner. The NFTs are stored in pages connected to the account that owns the NFT. This is efficient for RippleD. This is all RippleD needs to be able to process NFT transactions. But users and devs and apps want to be able to look up an NFT by ID, right? They want to be able to say, given this token ID, give me this NFT. But to do this in RippleD, you would actually have to scan the whole ledger. Because if you don't know who owns it, right, you have no idea which account owns it, you have to walk through all the accounts, right? This is going to take a long time. It's going to take at least 20 minutes, probably much longer, right? So it's like a no-go. So we added this to Clio, though. So in Clio, what we do is whenever we see some transaction that affects an NFT, we parse out the token ID from the transaction, and then write the NFT with its metadata to a database, keyed by the token ID. And then Clio nodes can serve traffic and say, oh, you want to know something about this NFT with this token ID? Let me look in this table and return it to you. So this is just a example of the code that you would need. On the left, it's this is how much code you would need to scan the ledger for an NFT. Not to mention this would just take so long, 20 minutes or more, versus just calling the NFT info, which is this API I'm talking about from Clio, is very simple. All right, so I'm actually going to demo this to you guys. Is this visible, or does it need to be made bigger? It's almost too big. Oh, it's too big? No. Oh. All right, is it somewhat visible now? No, that's good. Okay. So, yeah, there's a Clio node running on the NFT DevNet. So let's get some random NFTs. So I'm going to call ledger data, which is a RPC that walks through a ledger, or part of a ledger. And I just filtered by NFT token page, so I can get some random NFT IDs. All right, so here's this NFT right here, just a random NFT. So Greg Weisbrod actually implemented this, so shout out to Greg. All right, so then I want to look this up, so I call this command called NFT info, and I put in that token ID that I just copied. Right, here we go. Okay, and it tells me about this NFT. I was able to look it up directly. It has an owner here, right? So let's actually check to make sure this is correct. So copy this owner. So this is the account that owns the NFT. I was able to tell me that. And then I can use account NFTs, which is what RippleD supports. And I can check that this is actually correct. All right, I think that looks like it. Yeah, it's got some NFTs. Just double check myself here. Make sure I'm not lying to you. Grep for this. Yeah, and it's there. It showed up with grep. I don't know if you guys know how grep works, but it's there. All right, that's what that means. Okay, so Another RPC that I added is support for ledger diffs. This is super helpful for a variety of use cases. So what a ledger diff is all the state objects that have been added, modified, or deleted as part of applying the transactions in that ledger, right? This is super useful because basically you can like keep some data set up to date by just walking through ledger diffs. So you would get like a base data set by walking through a whole ledger, and then just extract diffs one by one and do whatever you want. Super general purpose. You could do a little bit of this with, well, you could do this with transaction metadata as well, but this is like a much cleaner way of looking at it. You get the full object every time instead of just like change fields, and it's easier to just take it and write it directly to a database. So this is part of the ledger RPC, and you just pass a special flag. So I actually demoed this too. So I have to send this directly to Clio. So this is s2.clio.ripple.com. Well, first I'll just send server info. Oh no, that didn't work. Oh, I forgot a quotation. So this is my Clio server. This is S2. This is publicly available. Anyone can hit this. This is talking about the cache here. It says the cache has 15 million objects in it. That's how many objects are on the ledger right now, by the way, 15 million objects. So yeah, I want to send ledger diff. So, yep. So this is like a list of all the objects that have changed. So I got some object here. Here's all the fields, all the data of it, and here's its object ID, right? It's just, I don't know, there's a bunch of these in here. It'll even show you when objects are deleted as well, right? This is some directory node that changed. Lots of these are directory nodes. So this is super useful. There's an account. So anyways, yeah, wrapping up here. So what's next for Clio? We're developing a new API, and it's like more consistent because the current API is really like, was developed like haphazardly and is super inconsistent, and like the same data has like a slightly different field name with a different request or a different response. It's a huge pain to code and code against. We want to add support for pathfinding, which is like how to exchange one currency for another, like what's the most efficient path. This is not supported in Clio. You can only do it through Ripple D, but it'd be nice to add this to Clio as well. On the performance side of things, I'd like to add support for an embedded database, so that way you don't have to run a database server. Obviously this has caveats, because then when you want to spin up new nodes, like you would need to copy data across. But with the caching that I talk about, I don't know, you could do something fancy where you can spin up nodes that are just cache only, right? And they just can like sync their cache off the existing server that's running with the embedded database. So maybe you could have a couple nodes that have the embedded database and a couple nodes that don't persist any data and they're just cache nodes. So you could get a lot of throughput there without always having to copy data. And the other idea is to actually run this without Ripple D, to just extract data from the peer-to-peer network, right? And like verify. You have to verify here. Because right now, like when you run Ripple D, your Ripple D node does the verifying and you trust your Ripple D node. But if Clio is doing this, we'd have to add a lot of code for it to actually verify the data that it's getting from the peer-to-peer network to make sure it's not like, being lied to. But this would be nice. Like if we do both these things, then all of a sudden you don't have to run Ripple D, you don't have to run Cassandra, you just run a Clio node and it just can handle your API, right? So yeah, that's that. Yeah, here's where the code is. It's open source, anyone can contribute. I'd be happy for you to help. And if you want to hit Clio, besides running your own Clio, we have Clio running publicly in S2. It's s2-clio.ripple.com. Sometimes we take it down for like different testing things and stuff like that, but it's up there, right? And soon we're going to move all of S2 over to Clio, right? So yeah, any questions? Jackson? Oh, right now it's just like the current validated ledger. Yeah. We could add support to compare it to arbitrary, but that would be a little weird. You'd have to like squash a bunch of diffs together. But yeah, that's definitely possible. Is that a use case you need? You're just curious? Okay. Okay, cool. Any other questions? Okay, cool. Thanks, guys.